Good morning, ma'am. My name is Pavan Krishna, and today I will be presenting my project, which is protein secondary structure prediction. This is part of work for intelligence of biology systems too. So, proteins are critical to life functions, and their structures determines their function. Secondary structures like alpha helix and beta sheets are particularly important. Traditional lab methods for predicting these structures are expensive and slow. So, this project proposes a hybrid computational model that combines Chow-Fasman and GOR algorithms. These models are rule-based, explainable, and computationally efficient. We also enhance beta sheet predictions using beta program and validate accuracy using standard datasets like CAT and DSSM. This presentation will cover the following areas. First, an introduction to the problem and why it matters. Next, the project objectives. Then, the background on existing methods. After that, we'll look into the methodology I followed. I'll show you the current status along with the short demo code. Finally, I'll wrap up with the summary and references. The importance of protein structure. Proteins perform vital biological functions like enzymatic activity, immune responses, signaling, and structure roles. Their function heavily depends on their structure, especially the second structure, which includes alpha helix, beta sheets, and coils. The motivation for the prediction is that predicting these structures computationally is essential because lab methods like X ray, NMR, and crystallography are expensive and time consuming. While AI based models exist, they are resource heavy and often lack interpretability. A hybrid rule based model offers an efficient and interpretable alternative. Objectives of this project are 1. To develop a hybrid prediction model by integrating Chow-Fasman and GEO techniques. And the second is to use beta program and hydrogen bond validation to improve beta sheet accuracy and use hash tables and parallel processing to enhance the computational efficiency. And the fourth one is to validate the predictions using DSSP to get the ground truths from the CAD dataset through Q3 and SOV scoring. And finally, the fifth one is to visualize the predictions using 2D sequence based plots. The importance of secondary structure. Proteins don't function just as a raw sequences. They need to fold. The secondary structure is first level of folding that introduces meaningful geometry through helices, sheets, and coils. These structures form a bond of enzymatic sites, binding pockets, and structural frameworks. Accurate prediction of this layer allows us to infer protein functions, design new drugs, and simulate biological interactions computationally. Experimental methods versus computational methods. Experimental methods have high accuracy, but not scalable for large scale protein analysis. This is where computational techniques come in. Early methods like Chow-Fasman and GR provided rule-based and statistical predictions that are transparent and fast. While AI models today are highly accurate, but they behave as a black boxes and require large labeled datasets. Our project focuses on enhancing these classical models for better accuracy without compromising interpretability or speed. The Chow-Fasman method is based on statistical likelihoods of each amino acid forming a particular structure. It is fast, but limited in context awareness. GOR, on the other hand, evaluates the residue environment using a window slide model and improve the predictions through the context. The beta program adds another layer of validating the beta sheet predictions using biological constraints like hydrogen bond geometries and strand alignment. These methods provide a solid foundation for hybrid model that is explainable and efficient. Methods overview of hybrid pipelining. The first step is to extract the protein sequences from PDB file from CAP40 dataset, which I have been using, but it does not have the ground truths about what the real secondary structure is. So we use DSSP tools to generate DSSP file which contains secondary structure and alpha value, etc. And then we use these raw protein structures and the raw protein sequences and run two classic algorithms like GOR and Chow-Fasman. These predictions are then improved using domain-specific beta sheet rules. Additionally, we incorporate a spatial hydrogen bond validation, which adds 3D awareness. All predictions are combined using tunable alpha value and then validated against real secondary structures using accuracy metrics. Finally, we visualize these outcomes to aid interpretation. Chow-Fasman algorithm is one of the earliest and most interpretable method. It uses empirically derived tables of amino acid propensities to predict structures. These algorithms searches for nucleation regions, 6 amino acids for helix, 5 for sheets, and check if the sum propensities across a defined threshold. If so, it marks those regions and attempts to extend them based on nearby residues. This method is simple, fast, and provides a strong foundation. GOR, or the Granier Osgood Robson model, builds on Chow-Fasman by integrating the surrounding residue information. It uses 17 residue window to consider each amino acid's environment and calculates the likelihood of forming a helicase, sheet, or a coil using statistical profiles. This model corrects for false positive and adds context awareness that Chow-Fasman lacks. It particularly effective in distinguishing ambiguous regions. After the initial prediction, we enhance beta sheet detection through beta program like rule system. Certain hydrophobic residues are likely to participate in these beta sheets, especially when flanked by predicted sheets. Additionally, we go a step further by validating hydrogen bonds using proteins' actual 3D atomic structure. We examine geometric features like NO distances and angles, which are in DSSP file, filtering out the residues that fail to form realistic hydrogen bonds. This brings a biophysically grounded refinement layer to our model. About the current status, the implementation is currently functional and progressing as planned. Here's a quick breakdown. First, we have built a sequence extraction pipeline which reads PDB files and DSSP files and correctly parses the amino acid sequence from PDB file and the true secondary structures from DSSP file using BioPython tools. I have extracted DSSP files from PDB files using a DSSP tool online. Then I have implemented the Chow-Fasman algorithm, which identifies helicase and sheet forming regions based on known amino acid propensities. This was followed by GeoA model, which adds context awareness corrections using 17 residue single window. Then these two models are combined into a hybrid prediction module, which is tunable with the alpha parameter, which blends predictions from both algorithms. A grid search is used to find best alpha value that gives the highest Q3 accuracy. To further refine the predictions, we applied beta sheet enhancement rules, targeting specific amino acid patterns likely to participate in the strands. We also added a 3D hydrogen model, the 3D hydrogen bond validator, that checks for proper geometrics using the atomic coordinates from the PDB structure, filtering out biologically unrealistic predictions. Once these predictions are ready, we compute Q3 and SOV scores to evaluate the accuracy of both residue and segment level. Finally, we generate a side-by-side visual comparison between the predicted and the actual structures using Matplotlib. This helps us visually interpret where the model is accurate or off. The screen recording will now demonstrate the code in action in the next slide. And this is what I have done. And this is the current status. And there are more further improvements in the future parts of the code, which will be done in the future. So good morning, ma'am, once again. This is the code part. So I have been using Cath40 dataset, which contains the PDB files, and XSSP server to extract DSSP file from this PDB file. So this is a basic code just to visualize whether we're able to open our PDB file, and yes, we are able to, and this is the format of PDB file which I have downloaded. So this is actually not the exact what do you say requirement required by the XSP file. So one of the key process step is preparing a clean and correctly formatted PDB file before we can extract secondary structure from DSSP. The XSSP server and DSSP software have strict input requirements, which are each line must be exactly of 80 characters long, and the element symbol like C for carbon and N for nitrogen must be placed correctly in the columns 78 and 79. So unfortunately some of my PDB files are lacking this formatting, so I have written this function just to format these PDB files which I have downloaded. And let's go with the code. So this code takes the input path and returns the output path with a new file which is formatted. I have downloaded for 34,000 PDB files, out of which I have been working on only two for now. In the future work, I'll work on everything and post it later. So this code, what it does is it takes in the path and reads it. It identifies the correct element symbol using basic heuristic based atom name, which are these, and basically it first goes through every atom and HETATM. Only these lines are considered because atom is what uh, every line starts with in the PDB file. So moving on, it places the correct element symbol at the correct location. This is what the code that places them, and the pads it pads the line exactly to the 80 characters required by the DSSP server. So this code makes sure about it, and finally writes the clean file to the disk. And this is the code which writes the new formatted PDB file. And that's it about this code. And this is the code which takes in the input folder, and the output folder is just a new folder. So what it does is, it's a for loop which goes through which iterates through 34,000 files which I have downloaded, and formats everything using the function above. And let's go to the main part of the code which implements the algorithms. Okay, this is it. Just a second. Okay, so this is the code which I have written, which is working currently. And what I meant to say is, this function these are the imports required: numpy for the mathematical purposes, and biopdb, which has the pdb parser which can pass the pdb file, and dssp parser for dssp file, and neighborhood search and vector. And from pdb polypeptide we are importing a pp builder, and matplotlib for plotting the secondary structure, and default dict is just a dictionary, and hashlib, which is used later in the code for improvement in the code, like working faster using hash maps. And OS is for taking inputs and outputs in the OS paths, and the loggings are for just giving the messages about where and at what time these functions are implemented. So let's start. These are propensity tables of Chow-Fasman, which has corresponding values for each each sequence structure in the PDB file. These are the amino acids in the protein sequence, and this is GR propensity table, which is containing the HEC turns only, the helicase and coil, etc. For each of the amino acid, which are 18 or 20, I guess. I don't remember exact number. And this is a caching hash table, just for faster for faster my bad. This is a caching table which is made of hash table, which is for faster accessing, which will reduce the overall time complexity. So this is hash sequence function. This function has a string using MD5. It is used uniquely to identify windows in the sequence. So we can cache previously computed predictions, boosting the speed and reducing the redundant computation. And this we use this exactly for caching intermediate predictions during Chow-Fasman and GOR runs. This allows us to skip recomputation when using the same window and improves the performance significantly. And This function parses a PDB file using BioPython and extracts the amino acid sequence. This uses PDB parser and polypeptide builder to extract linear amino acid sequence from the PDB file. It is the first step in our pipeline and provides the input for the prediction models. And this is the function which extracts the secondary structure from the DSSP file according to the PDB file. The DSSP is the gold standard method for annotating secondary structures from 3D protein data. This function reads the DSSP output and extracts the experimentally assigned secondary structure, which we later compare in our predicted output to calculate Q3 and SOV scores. These are the valid turns, like structures which it can take, which are in the PDB file. So I've included all those, but mostly we'll be using HEC only for now. And this is the full Chow-Fasman function. Let's go through it. The full Chow-Fasman function applies the classical rule-based algorithm. It starts by detecting the nucleation zones, while helicases or sheets are likely to begin based on summed amino acid propensities. Then it extends these predictions to nearby regions, and this provides our first pass of prediction and is cached for performance. And the next function is GOR function. GOR is a statistical method that uses information theory. The function full GOR slides to the 17 window across the sequence which is given to it as input, and it computes the probabilities. It computes the probabilities for each structure type based on the surrounding residues. This context awareness correction is particularly useful for resolving ambiguous regions that Chow-Fasman might misclassify. And this is beta program enhancement code. It is function that enhances beta sheet predictions by identifying the hydrophobic amino acid flanked by sheets. This enhancement step mimics the logic of beta programming. A certain hydrophobic amino acids like valine, isoleucine, and tyrosine are commonly found in beta sheets. If such residues appear between two predicted sheets, they are also marked as sheet to fix under predictions. This is some of them which I have said: valine, isoleucine, and tyrosine, and some more. And this is coil. If it is predicted as coil, then we'll consider it and return the enhanced, the list. And the next function is refine hydrogen bonds for sheet, which takes in the PDB file and predict it. So first we check the hydrogen bond geometries from the 3D PDB structure to confirm or reject the sheet predictions. This is one of the most biological grounded steps. It uses Python spatial search to detect hydrogen bonds. If a residue predicted as a sheet doesn't form a proper NO hydrogen bonds within a 3.5 A Armstrong and with the right angle, we discard the prediction. This step adds a true structural validation for our model. This is the part of the code which checks if it has hydrogen bonds, and if yes, this is the code for what are the like distance between the HN atoms and ON atoms, and we use the vector to vectorize them to get angle. And if the angles are between 150 and 180, then the hydrogen bond is found, else it is not. We might discard it. And we need, if the hydrogen bond is not found, we'll redefine it as a coil. And moving on to next one, this is a function which takes in the sequence and alpha value and combine like it is the hybrid model combining the Chow-Fasman and GOR. So if GOR using a weighted score determined by alpha, so it runs in a for loop which has the Chow-Fasman GOR written values, and this hybrid function merges the predictions of those both using a tunable alpha parameter. If the alpha is 1, the output depends entirely on Chow-Fasman. If the alpha is 0, it fully depends on GOR. This is flexible integration which allows us to tune the model behavior based on the performance. This is nothing but the value of alpha into, if it is H, is predicted in the Chow-Fasman, into alpha, which is the present H. Like it's just having a scores from Chow-Fasman or GOR based on the alpha value to predict the present secondary structure, which is helicase or E or coil. That's it. And the Q3 prediction, which is accuracy matrix, it calculates the Q3 accuracy, the percentage of residue correctly predicted as HEC. That is how many positions we correctly predict out of total. That is a standard metrics for evaluating the secondary structure model. And moving on, SOV is a segment overlap score, which is a more sophisticated matrix that compares predicted versus actual contiguous structure region. Unlike SQ3, unlike Q3, SOV evaluates how well the model captures entire segments or domains of a structure. It is important because of a model might predict a right type but a slightly wrong position. So SOV counts for this and gives us more realistic evaluation. And we use grid search, which takes in sequence, true and alphas. We perform grid search across different alpha values to find one that gives the best Q3 score. This function automates the tuning of the hybrid model. By testing different alpha values, we identify the blend that gives us the best Q3. This removes us the guesswork and helps us find the optimal balance between Chow-Fasman and GOR. And coming to the visualization part, this generates a normal visual heat map comparing the predicted and actual structures. We finally visualize the result at the bottom like this, which actually show this is the actual DSSP structure and this is the predicted structure, and you can see the differences in the color. The same color determines that these are correctly predicted, the different color says these are different, like the prediction differs. It is a quick way and effective way to visualize. And that's it. The explanation. What do you want more? This part of the code, yeah, here. This part of the code takes the PDB file and DSP file. We are doing presently on the single PDB file, which is a single protein structure. In future, we'll be working on 34,000 protein structures and get a final output for all of those. And this main execution pipeline, it validates the path and extracts the sequences and structures. It extracts the sequences of from PDB file and true ground truths from the DSSP file according to the PDB file protein sequence. And it takes alpha values from 0 to 1 with 21 different instances. And best alpha and best Q3 are taken from the grid search alpha function, which I have explained before. And it just prints the best alpha and Q3, which are the best alpha is 0.5, which is exactly the middle, and the best Q3 which I have gotten for this PDB file is 54 percentage. And the hybrid model predicts for both Chow Fasman and GOR, and it is refined based on the hydrogen bonds which we have seen before. And the evaluation matrices are Q3 and refined Q3. Like Q3 is just by taking this one takes just the hybrid model output, and this takes the refined hybrid model output based on the hydrogen bonds. So the difference, it made nothing in this file. It may make difference in the future files, which I'll be checking on later. And I also taken for the SOV the hybrid model output and the refined hybrid model output, and both of them didn't differ much, which are of 54 percentage. And this is the visualization at present I have made. I'll be working on this visualization and more of the code to improve it, and will try to get suggestions from you in later future. Thank you, ma'am. To finally summarize, this project delivers a hybrid rule based system for secondary structure prediction, which is fast, interpretable, and fairly accurate, but not accurate as the ML models. It bypasses the limitations of deep learning while leveraging the classical biological bioinformatics algorithms. This model will be validated with real biological data and visual outputs. The references part, the work is grounded in foundational research from Chow Fasman and the GOR group. The beta program is used for rule-based validation for beta sheets, and dataset references include DSSP and GAT40 for benchmarking. And these are the links provided in the PPT.